Hey, greetings everybody. Hey, welcome to chapter 6. This is Atoms and Spectra, and this is the first chapter in unit 3 on the stars. We're making real progress here. Here we're actually looking at a model of the atom where we have the nucleus here. That'll be composed of protons and neutrons. Protons are positive charges surrounded by electrons. This is sort of the quantum mechanical view where we have probability clouds for the electrons. We don't know exactly where they are. They're negative charged particles. Okay, so this is just an intro to the atom a little bit, a few terms you've heard, but we'll remind you of them again. An isotope simply means that an atom has extra neutrons. For example, oxygen, O16 versus oxygen 18. That means that this guy has two more neutrons. These two things are the same element, okay? They both have 8 protons, but some have a couple more neutrons. Ionization. This simply means when the number of protons and electrons is not equal, the atom is charged. An atom can either lose an electron or it can gain one, depending on the situation. Either way, that's called ionized. The whole atom becomes charged, has an electric charge. Molecule. This is when you have two more atoms bind together. A common example of this is oxygen. Over 20% of the atmosphere that we're breathing right now is composed of O2, that very common little molecule consisting of 2 oxygen atoms. Coulomb force, this is the force that binds the electrons to the positive nucleus. In other words, this is what keeps atoms together. Without the Coulomb force, the electrons would wander off into space and they'd leave a lot of lonesome positive charges in the nucleus. All right, now let's talk about how radiation works. Here we have the nucleus right here in the center. These things right here are energy levels. They're showing you 1, 2, 3, 4, 5. They're numbered that way. And here's the secret quantum secrets that you need to know. Electrons are only permitted in certain levels. That means you can never find an electron here between this level and that one, or here. They have to be on the levels themselves. Second thing is electrons can transition between levels. This is simple quantum physics. And the energy will be either emitted or absorbed depending on what happens. Now let's talk about that. Oh, I just realized my little rectangle in the lower right is actually covering up the spectral line. I forgot that was going to happen. But let's go ahead and take a look at this anyway. Here is, this is a transition. The electron is actually jumping down from this level to this one. So that means he's going downstairs here. He's losing energy, and so that means a photon will be given off, but it won't be a big photon because this is not a very big energy jump. So this gives off a low energy photon. In this case, it's red. Okay. Now let's look on the other direction. Way over here, we've got one originating way out here. It goes through 1, 2, 3 energy levels. That's a lot of energy. That's going to be a big photon. That means it has to be violet. You should remember that the reddish photons have low energy and the violet ones have lots of energy. And this is what causes spectral lines, these very discrete transitions between the only energy levels that are permissible in this particular atom. Now, the energy levels are different in all different atoms, okay? This happens to be hydrogen, has 1 electron and 1 proton. But other atoms have somewhat different energy levels, so they have different spectral lines that are actually forming. Okay, speaking of spectra, this is what the sun spectra looks like. The sun spectra actually has thousands of lines in it. This is just simplified so you can get the picture. And you can see these spectral lines are associated with certain wavelengths, and that is telling you that they are associated with certain transitions in the atoms we're talking about. Like, for example, this line and this line are both due to oxygen. And this one is a little lower energy line than this one was. Notice there are hydrogen lines throughout this thing. These are due to actual transitions that electrons are making in the hydrogen atoms. Notice there are also iron, that's Fe, magnesium, that's Mg, and calcium is over here, several calcium lines. So this is what a spectrum actually looks like. This is an absorption spectrum. It means that the photons were actually absorbed and made the electrons jump from lower levels to higher levels in the atom when this transition occurred. Okay, here is a big deal. This is black body radiation. Stars are black bodies, which means they emit pretty much the amount of energy that they absorb, and they're very tidy in that sort of accounting. But here's obviously, this is, we're plotting the intensity of light versus wavelength on the x-axis. The wavelength of light. Notice they're showing you the visible spectrum here, violet to red right there. But notice we got 4 stars here, 1, 2, 3, 4. They're actually showing you the energy distribution with wavelength for all 4. This is a hot star at 6,000 degrees. By the way, that's close to what the sun is. This is a somewhat cooler star that's 5,000 degrees. Notice that it's a completely different black body curve. And this is another star that's even cooler, 4,000, and another star that's cooler, 3,000. So the 3,000 is way down here. The 6,000 is way up here. So the higher this curve is, the more energy is given off. That's what it means by the intensity of radiation. So the first thing we notice here is that hot stars, namely guys like this, give off more energy than cool stars. This guy's way down here versus the guy who's way up here. Much hotter, much brighter. So hotness and brightness go together in the star business. Now there's another thing that's important here. By the way, here's the actual formula. You don't need to know this. It's just on the graphic. Now, let's take a look at the peaks of the radiation. Notice the 5,000 peak is right, actually, they're actually showing us with this cute little blue curve. The 4,000 peak in the radiation is right there. The 5,000 is right there. Notice that's a different wavelength for the 4 to the 5,000. And the 6,000 peak is way up here, another different wavelength. And it turns out all we have to do is measure where the peak of the radiation is for any of these stars. And once we know where the peak is, meaning once we know where that wavelength is, where the radiation peaks, we can actually use that to calculate the temperature of the star. A very powerful thing. Let me show you how that works. Here's a couple of laws. These things are very useful. Here's Wien's law. This is the one that says the surface temperature of a star is equal to some constant K divided by the lambda max. The lambda is the wavelength. The lambda max is the wavelength of the maximum radiation. So all we have to do with our little scanner, I'll go back here. All we have to do with that little scanner, or I won't go back there, is find where the max radiation is, make note of what the lambda max is, and we have got the temperature. Powerful stuff. Now, for any star, the amount of energy given off in all wavelengths is simply equal to a constant called sigma times the temperature of the star to the 4th power, T to the 4th power. So that means the energy is a very strong function of the temperature, not surprisingly. Here's the Doppler effect. I'll bet some of you guys are familiar with this. Almost everybody's familiar with it. They may not realize what it's used for. This is a way that we can actually measure the speed of objects coming toward us or going away from us by doing a very simple thing. Let me show you how it works. These are actually spectra. These are make-believe spectra. And this is the no shift position. Now, if you have an object that is moving away from you, we'll say it's receding from you. What happens is that you get a redshift. Notice the lines are actually displaced toward the red, which is over here. All of them are displaced toward the red. And by measuring this redshift, so-called, we can actually measure the speed of the object that's moving away from us. Very powerful stuff. This stuff is being used right now all over the world to study dark energy and to try to develop a 3D map of millions of galaxies so we can figure out what dark energy is. And I'll tell you more about that shortly downstream. If the object happens to be coming towards you, that isn't that common when you're dealing with galaxies, then you get a blue shift, and you can do the same game. Just measure the shift, and that'll tell you exactly how fast it's coming towards you. And